Greg, and this is my friend Hank, and we're in town for the Giant Jamboree because we wanted to learn a little bit more about synthetic biology. But Hank is Taiwanese, and it's his first time in America, and I heard he's gotten into some trouble. What's going on?
At first, very good, but no money. Live on street. Dirt poor.
Oh, you're dirt. Okay, well, first of all, that's not dirt, that's soil. And second of all, you're in luck because our team is working on a project that could help you turn that soil into millions of dollars.
But how?
Okay. Well, our project plan B is a smart farming system that uses artificial intelligence in order to solve one of the biggest problems in agriculture, imbalanced soil microbiota. Through AI, we're able to achieve self-learning models that get stronger and stronger over time, delivering true precision agriculture and getting the soil to do exactly what you want. Let's take a look.
Oh, it's so itchy. Oh, hello. I was just working on our farm over here, and I don't know if you realized, but I just got stung by a mosquito, and right now my leg is very itchy. Now my leg is itchy because it's trying to tell me that I've been affected by some sort of external stimulus. And just like my leg, the sensors here that we use on the farm must be extremely sensitive to any sort of condition that might affect our crops. For example, weather, fertilization, and even pests. So let's go on a journey to find out what sensors we use on this farm and how they protect our crop health. Let's go. Our weather station gives us the weather forecast. It contains sensors that detect conditions such as light intensity and UV radiation. In addition, it also contains our Arduino UV sensor. This is where all of our data is collected. This is our pH sensor. Conditions such as soil moisture and weather events can cause shifts in pH and affect the soil environment. This is the device we constructed this year. Underground is a multi-function sensor which can detect electrical conductivity, soil moisture, and soil temperature. We've attached a solar cell panel on top, so our device is self-sufficient. We use a drip irrigation system to minimize waste of water. This system is also used to dispense our biostimulators, which can precisely regulate our soil. Arduino UV is the foundation of our hardware. This is how we collect the data from our sensors and transport it to our IoT platform through the internet. Artificial intelligence allows our models to self-learn the various conditions and factors of our soil. Calibration of models with real data improves accuracy over time, leading to strong prediction capabilities and even more robust soil. So now we've learned about all the systems we use in order to monitor the different conditions that might affect our turmeric growth. Using this, we can not only adjust the way we fertilize and supplement our crops next time, we can use the data in a feedback system, using artificial intelligence to increase prediction accuracy for the next time. We hope this video helped you understand our project a little bit better, but now I have to get back to my itchy leg. So itchy.
So, what did you think about that?
Don't understand how to get what I want.
Okay, well, it's okay. Let me explain a little bit more simply, because you don't need to be a scientist to use our system. In fact, let's just pretend you're an actual farmer who wants to use this. Let me take you and the rest of the audience on a journey to making you a millionaire. First, we start by understanding your soil, specifically the bacteria in your soil. Now, this isn't emphasized enough currently, but farmers have to pay attention to two important types of health. The first is crop health, which we all know about. The second kind is soil health. While fertilizers determine how well your plants grow, it's bacteria who determine how healthy your soil is. How? Well, since the beginning of life on Earth, bacteria have been some of the most powerful and influential organisms, shaping the very environment they exist in, and it's no different in soil. Levels of macro and micronutrients in soil are all determined by bacterial metabolism. Adding fertilizer with only the few nutrients that help plant growth does nothing for your soil health. In fact, it lowers it by skewing microbial distribution. What you really need for soil to be healthy, is a balanced microbiota.
So, too much fertilizer, no balance, and you want to reset the balance.
That's exactly right. We're going for a hard reset. And so we start by collecting next generation sequencing data, or NGS, of your soil. This tells us what kind of bacteria are in your soil based on the genomic material that we find. Then we organized our data into a stacked bar chart, which is this one, which tells us the exact bacterial ratios in your soil. Finally, from this we can calculate your soil microbiota evenness, which can be used as a general indicator of soil health. Higher evenness indicates healthier soil and a more balanced microbiota.
So even is good, and you want to increase it.
Exactly. That's what we'll keep in mind when we add our biostimulators.
Wait, bio what?
Oh, biostimulators. Yes, let me explain. Biostimulators are basically anything that increase crop growth or soil health by altering bacterial distribution in soil. They can include anything from fertilizers to peptides.
But predict biostimulator change is too hard.
He brings up a very good point. It's incredibly difficult. In fact, if you ask any traditional ecologist, they'll probably tell you there's too many difficult and complex interactions to consider in soil. But that's why we're not using ecology. Instead, we're integrating the power of machine learning to accurately predict how all of our biostimulators will affect the levels of bacteria in soil.
Machine learning. Software learns how bacteria behaves, right?
Exactly. The point is, software does all the hard work for us. So we can forego any conventional biological analysis and use purest math to simply explain what's going on in soil.
That's very cool, but can you prove it?
I'm glad you asked, Hank, because this year we used real soil samples and NGS data collected from our farm to construct a model that basically describes the relationship between nitrogen, phosphorus, and potassium fertilizers and our soil changes. But rather than talking about it all day long, why don't I just show you? All you need to do is input the values for each nutrient and press predict.
That! Oh my god, it's amazing!
It is, isn't it? Now, for a regular microbiologist, that would have taken a lot of time and even more effort to calculate by hand. But you did it in just under 10 seconds. That's the power of machine learning. But let's not stop there, because the purpose of our model is to predict not only how bacteria change, but the ecological impact that they bring. So let's analyze our soil samples before and after Hank's input. Oh my God, our evenness decreased. Of course it did. Don't be surprised, okay? This is what happens when you enter a random combination of fertilizers like Hank did. But to this day, farmers are doing exactly that. They fertilize based on experience, and they don't know how exactly the fertilizers are influencing their microbiota. Until now. By using this model, they're able to understand exactly what fertilizers to put in to influence their soil bacteria. And through this, they can adjust their volumes accordingly. Now, Hank, do you remember the part where I talked about artificial intelligence in the beginning?
AI, self-learning?
That's exactly what artificial intelligence is. In fact, AI is nothing more than the feedback of data back into our models in order to strengthen them and their accuracy. So our initial microbiota prediction model requires 2 sets of NGS data, one from before fertilization and one after. But our initial prediction accuracy is pretty bad. In fact, it's only 51%, which is far from ideal. However, fitting in a 3rd set of NGS data allows us to calibrate our models to the specific soil conditions, increasing accuracy to 78%, which is a lot better. Using artificial intelligence strengthens our model's precision by allowing it to account for soil conditions that we may have missed otherwise. In fact, if we put in a theoretical 4th set of NGS data, you can see, according to the trend of our learning curve of microbiota prediction, our accuracy would increase to 90%, making our model much more reliable.
That's very nice, but when to add more?
Okay, so Hank is wondering, since we know the volume of application, we don't know the application frequency, and they're actually 2 sides of the same coin. If you know one but not the other, you're still left with unhealthy soil because you don't know how much fertilizer to put at what time. But we have thought of a solution. Let me introduce to you our EC sensor. Now, EC, or electrical conductivity, is basically a value in soil that can be used to determine how much nitrogen, phosphorus, and potassium fertilizer is left. So using this, we constructed another model, this time describing the relationship between nitrogen, phosphorus, and potassium fertilizer and an electrical conductivity reading. Then we constructed our device, which is basically an EC sensor connected to an IoT talk platform. From this, we can continuously feed data into the cloud, which can then be used to alert us should our fertilizer drop below a certain level.
Wait, can IoT help make AI stronger?
You're beginning to understand the backbone to our project. Artificial intelligence is the backbone to our system, and As Hank just suggested, the IoT Talk platform is a way to strengthen this artificial intelligence. Data that is already automatically fed into the cloud can be refed back into our models, making them much more precise. In this way, farmers can know exactly when to refertilize, thus cutting down on fertilization waste. That is the brilliance of our system. By combining microbiota prediction and our EC model, farmers can know exactly how their fertilizers impact soil microbiota. From this, they can determine application volume as well as space out their application frequency, thus supporting healthy plant growth while giving soil enough time to recover. This helps them maintain soil integrity.
Wow, your system solves many problems. This dirt can make me rich.
Okay, again, it's soil, not dirt. And yes, it can, and I really appreciate your enthusiasm. But we're not done yet, because the soil that you're holding in your hand right now still has a lot of problems. Years of over-fertilization has led to heavy accumulation of certain elements that might skew your microbial population. For example, by making certain bacteria too dominant. But don't worry, we've got your topic covered too. Now I'd like to introduce Evelyn, our protein expert, who will explain a new kind of biostimulator we've been working on.
Hi Hank, I understand that you have a soil problem and I'm here to help out. Interestingly enough, the best way to inhibit the growth of bacteria is by using the peptide produced by another bacteria. Different species and strains of bacteria produce antimicrobial peptides called bacteriocins to gain a competitive advantage over other bacteria. These bacteriocins are pH and temperature stable and they grow quickly, providing little threat to the environment. More importantly, they target specific membrane structure that vary from species and species and are extremely specific, making it ideal for our precise control of key bacterial groups. Let's take phosphate-solubilizing bacteria, or PSB, for example. Overuse of phosphate fertilizers has led to rapid growth of PSBs, specifically Bacillus subtilis in the soil. When excessive, they cause the serious oil acidification without a real solution until now. We are going to use bacteriocins to inhibit the growth of Bacillus subtilis to demonstrate the use of peptide as one of our biostimulators. We use storing time to choose these 6 bacteriocins and construct the following bell bricks, consisting of a T-cell promoter, ribosome binding site in our peptide sequence, followed by inting and codifying domain for purification. I will verify correct expressions through different experiments. We want to be able to inhibit our PSB precisely so that the appropriate amount of bacteria will be left in the soil to support plant growth without being excessive. To do this, we start with interleucin B as an example. First, performing inhibition zone to test the function. Next, doing inhibition ability analysis to determine the relationship between concentration and degree of inhibition. We do this with other bacteriocins successfully as well. Then we construct the growth curve of Bacillus subtilis under different pH, temperature, and salinity values. Finally, we combine our growth curve with inhibition results to generate bacteriocin effect models. Additionally, we assess safety. After high temperature sterilization, our peptide is still present without bacterial growth.
Soil health, very nice. But how do plants grow?
All right, I like the way Hank thinks. Basically, he is asking whether or not we can make money with our system, because we can do all the regulation in the world, and it would be meaningless if we couldn't keep up with our productivity. So to demonstrate the efficacy of our system, we combined our microbiota prediction as well as our EC model and used it on a real farm to grow turmeric plants. We chose turmeric because it's a high-value crop that heavily depends on soil health and adequate nutrients to grow well. So if we find out that our turmeric grows well, we know that our system has been correctly designed. First, let's begin with our soil changes. Over the past 4 months, we've applied fertilizers as well as biostimulators to enhance our soil. From the graph, you can tell that good bacteria, such as nitrifying bacteria, increased, while harmful bacteria and bacteria that indicate pollution decreased. Additionally, our evenness increased, even though we regularly fertilized. How is this possible? Well, using our system, we were able to determine the volume of fertilization as well as the application frequency in order to maintain our soil health. That way, our turmeric grows well and our evenness does not decrease. Rather, it increases, making our soil even healthier. Next, let's move on to the plant product, which is what makes our money. Curcumin is the valuable and active ingredient in turmeric, and we want to know how much we can extract from the roots before we harvest to know how well our plants have grown. To do this, we constructed a model that describes the relationship between nitrogen, phosphorus, and potassium fertilizers and final curcumin concentration. From this model, we can determine our final curcumin yield based on total amount of fertilizer used up until this point. And finally, we need to be able to measure the amount of curcumin in our plant. But we didn't want to harm our plants by pulling them out of the ground too early. So we designed a curcumin biosensor using a bovine milk protein called alpha S1 casein, which has the ability to naturally bind to curcumin located in the plant's leaves.
Let me explain. The following composite boundary containing a T-cell promoter followed by a linker and alpha S1 casein. To verify our sensor's function, we perform pulse photometry. Because curcumin is a natural conductor, increased electric flows indicates successful binding to the target.
And through our constructed biobrick, we can confirm that turmeric grown under the influence of our system not only grows taller, but has a much higher curcumin concentration than other turmeric on other farms. Now, Hank, you probably understand the whole basis of our system by now, so I'll spare you the details. But basically, we've found another way to integrate artificial intelligence in our system by feeding back curcumin sensor readings into our model, making it more and more precise, and allowing farmers to know exactly how much total fertilizer to apply in order to achieve a final desired curcumin concentration.
Very easy. Let me explain. Build a model, use AI, model gets stronger, IoT make automatic, make a cycle that improves every part, and you'll know the total nutrient, how much at once, when to add more, and also increase soil health and crop production, right?
Eric, he explained better than you did.
But, do you get help to think of this?
Of course, the field of synthetic biology is dependent on sharing ideas and opinions and merging of expertise. We initially knew we wanted to fix the problem of soil acidification after a visit to agricultural improvement station. But it was so expert, Professor Yang of National Chongqing University, who pointed us in the direction of bacteria, specifically Bacillus subtilis. Once we visited the Asia Agricultural Technology Exposition, we discovered many companies use bacteria as soil supplement. And it was at that point we decided that microbiota regulation system would be extremely useful to the industry. Naturally, we want to compare with other teams, so we share our project with the neighboring school, National Tsinghua University, and they share them with us. We then visited each other's laboratory and performed various experiments to check each other's biobrick design. Additionally, we discussed how to compare our result in a more meaningful way. Through integrating human practice, we collect many ideas and suggestions to shape our project. And we construct many models to bring our project to fruition and use AI to strengthen our models. And of course, we demonstrate our result on a real turmeric farm, improving both soil health and curcumin concentration through regulation of soil microbiota. On top of that, we improved the biopesticide biobrick designed by NCTU Formosa 2016, adding a GS linker to improve the inhibition of pests.
Now, the field of synthetic biology is unlike any other. It combines so many different ideas and ways of thinking to solve problems previously thought unsolvable. This year, our project draws inspiration from the power of nature as well as the efficiency of machine to deliver a solution that finally solves the biggest problem in agriculture. Using biostimulators, we accurately regulate microbiota the way we want, generating self-learning models that get more and more accurate over time through feedback of information from our IoT sensors. We also expanded our concept to include bactericids, demonstrating the adaptability of our system to any problem in any soil on any farm. With this robust system, farmers will no longer have to choose between soil health and crop productivity. With Plan B, they'll easily achieve both through the precise regulation of soil supplementation, at the same time cutting fertilization waste and keeping costs low. And while this season of iGEM draws to a close, it's only the beginning of our project. Since 2014, our team has been developing novel and effective agricultural products, and combined we have over $2 million in company and government support, and we're ready to take our concept to the market. In fact, our startup is scheduled for the end of next year, and our goal is to expand the role of synthetic biology in the field of agriculture for many, many years to come. We'd now like to take the time to thank our instructors, advisors, as well as any experts and sponsors who helped along the way. We couldn't have done it without them. Finally, I hope we've helped to clarify the purpose of our project, and I really hope that my friend Hank finds a safe place to sleep tonight. Come with us as we cultivate a better and brighter future for everybody. Thank you so much for listening to Team NCTU Formosa's 2018 project, Plan B.
Thank you so
business who was selling their products. So how do you envisage this in the future? Is this available to more farmers? Because it's a complicated system with a lot of technology.
Okay, thank you for your question. And first of all, to our project and in the future for our startup company, we will focusing on the medical plants as a producer of raw materials. So we will cooperate with the contract farmers so they can afford our system. And in our system, they can optimize their medical plants. And the first medical plants that we will focus on is the turmeric plant, and followed by the other medical plants. The point that we choose medical plants because it's high value. So we can ensure that the benefits of the farmers. Thank you for questions.
Well, first of all, congratulations. It was a great and amazing job, and it was a great presentation. Well, I have first question. Did you measure any other molecule in the plant? I mean, for example, when you use this kind of technology, the plant produces, for example, hasmonic acid, phytoalexins, stuff like chemicals like that. Did you measure any kind of chemicals of metabolites, or just the vegetable part?
We measured the curcumin, the most important part, because this part, because the value of the product is about the curcumin for turmeric. So we only measure this kind. Thank you.
Great presentation, I really enjoyed it. For the microbiome predictor, then you need to know the optimal microbiome, and does that vary by soil type, crop, etc.? And do you have that information?
It definitely does vary by what kind of plant you're trying to grow. But as a general indicator, we look at evenness. So it doesn't matter what kind of soil you use, as long as your evenness is high, your soil is pretty healthy. And the point of that is to prevent soil problems such as acidification, salinization, and erosion. And then for the plant part, you would have to look at specific bacteria. For example, we use phosphate solubilizing bacteria, and you would probably have to calculate the exact percentage that you would want it to be at if your plant needed phosphate solubilizing bacteria.
Is that information that your company would provide?
We would definitely provide
Okay,
it, yes.
And the second question is just about the placement of the sensors. So in a field, how is this like how many square meters do you need to have a placement of a sensor?
Okay, thank you for your question. And for about 1 hectare areas, right now we estimate for 6 sets of sensors, including the pH, the temperature, and also the EC value. Because EC value is very important for our project right now, it's because for the fertilizer model to be up. Thank you.
Hi, thank you for your presentation. Looking forward, what additional parameters would you like to incorporate into your model?
So farming is actually influenced by a lot of different conditions, and right now we're only collecting information about pH, salinity, and temperature and EC. But in the future, for a more complete project, we would probably be looking at considering the weather, so real-time forecast, and because if it rains, it actually affects how much nutrients are in the soil, and erosion, the flow of nutrients out. So we would probably use something called CNN to integrate more information into our models and predict how weather events would impact how we apply our biostimulants.
Thank you.
Hi, great job, guys. I have a more complex question related to the biological explanation. Did you wonder why the curcumin, that is a secondary metabolite, is improved in the production in the case of a healthier soil?
Could you repeat the question?
So curcumin is a secondary metabolite for plants that normally is related to stress. So did you wonder why, I'm just asking for if you have some explanation for that, why the level is improved if the soil is better?
Okay, so you mentioned a very important part, which is that plants are heavily affected by stress, and soil quality plays a huge part in how stressed the plant is, because If the pH is too high or the salinity is too high, which is often the case because of over-fertilization, then the plant is unable to absorb nutrients, and it's a bad environment in general. So once we have optimized the soil layer, the plant is it can easily absorb more nutrients, and it can function better overall, and it basically increases the general health of the plant, which translates to more productivity.
Okay, one final question.
I just have one question. The bacteriocin, did you measure if it affects like the good microbes, let's say, for example, as so that you contact someone from Bacillus subtilis, I don't know if it affects Trichoderma, Bacillus subtilis, or so the one that's sitting